Let's get going now. So this is where, we left off a little bit below this, but just as a refresher, because it's been a couple of days, we're talking about loops. A while loop, it's like an if statement where the code indented runs, but it keeps running over and over and over and over and over until the condition, until the Boolean on the right of the condition evaluates to false. It runs whenever it's true, whenever that evaluates to true. And we saw, like last time for laughs, you could make it so the condition will never not be true, so it'll run forever. And similarly, we can make it so it's always false and it'll never run. But ideally, you want it to be like dynamic in the sense that it can do some calculation that's meaningful. So when you look at this code, take a moment, look at this code, don't yell out an answer. Give yourself 20 seconds to lock in an answer in your head. How many times will that loop run? You don't have to answer, but raise your hand if you've locked in an answer in your head. Perfect. Keep your hand up if your answer was, put your hands up if you have an answer locked in. Really high, really high, really high, really high. Don't put it down, keep it up. You had to switch? Oh. Keep your hand up. Hey, keep your hand up if you had 10 locked in. Right? I'm confused. Your hand went up after. Yeah, okay, good. Why 10? Well, it starts at 0. Is 0 less than 10? Yeah, okay, it runs. Add 1. Is 1 less than 10? Yeah. I know I said yeah. Ugh, true. And so on and so on and so on. But remember, once counter is 10 less than 10? No. False. Thank you. See, you're keeping me on my toes. It's true. It's Friday afternoon. It's Friday noon. So, yeah, we got to be careful here too, because a lot of times, remember, we start counting at 0. So you might say, well, it doesn't run that 10th time. Well, it doesn't run when counter is 10. Counter becomes 10, and then it won't run again. But it also ran for when counter was 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I only counted to 9, but all 10 fingers are up. So it ran a total of 10 times. Any questions about this, the idea of this loop here? All right, so here we go. Write a function. Now this one is, I want to be clear, this one's a little tricky, so I'm going to give you a few minutes to do it. Write a function called int sum that takes a single integer n as a parameter and returns the sum of all numbers between 0 and n inclusively. When I say inclusively, all I mean is you include 10 in the summation. So if I say 5, it should be, okay, 0, whatever. 1 plus 2 plus 3 plus 4 plus 5. So you include the 5. So write a function that will add up all the numbers between 0. I guess you could skip. Well, no. I want you to not skip 0. Add up all the numbers between 0 and n. Before you hit run, though, trace through the program that you actually wrote before you hit run. Write the code before you hit run. Trace through the code, line by line, and keep track of the values as you go to check if you're right. And then run it and see if you were, in fact, right. And if you weren't, find out where you got it wrong. So I'm going to give you a few moments for this one. This is a good exercise. Nope. Yes. Raise your hand if you're done. Raise your hand if you'll be done in like 1 more minute. Okay. I'm giving you a big hint. If you're struggling, here's a big hint. There, I fixed the hint. I had a typo. Now, if you did it a different way and it works and it doesn't align with my hint, that's fine. What did I do wrong? Oh, do I have this backwards? Am I doing my type hints backwards? There we go. Much better. Let's get rid of this. Raise your hand if you got it working. Raise your hand if you found it tough. Now, the reason it's tough is because I suspect the reason I think you found it challenging was because of the fact that we actually had two variables. There was a running total variable that we had to keep updating, and there was also a counter variable that we have to keep updating. And you might have kind of like not teased them apart. And this is another example of don't try to get fancy and make it work with one variable. You need a counter, make a new variable that's a counter. Keep it as simple as you can. Have each thing have its own purpose. Don't try to muddy it and make it more complex than it needs to be. In general, when you have a while loop, and it's like a counting while loop, something that's going to run for some number of times, you're going to want your while loop that is well, my counter is less than what I want to run till. You're going to want your counter defined, probably starting at 0. And you're going to want to increment your counter. So in general, a while loop has a counter, the condition for the counter, and your incrementing of the counter. That is independent from, independent might not be the right word, but it's separate from the fact that, well, every time through the loop, I want to add the current value of the counter to my running total, because the counter is going to go 0, 1, 2, 3, all the way up to n. So let's work through this code. I put in the number 0. Now, this last test case here, we could argue about. We'll get there in a moment. I put in 0. Okay, running total is 0, counter is 0. Before even looking at the code, what is the sum of all numbers between 0 and 0? 0. Did anyone try to cheat and start at 1, being 0 is useless? Really? I don't believe you. Come on. Usually people do, and it's careful. I said it starts, it could be between 0 and whatever, so you could have specified 0. Okay, so yeah, counter is 0. Is counter less than or equal to 0? Yeah. All right, add 0 to the running total. 0 plus 0 is 0. Add 1 to the counter. Counter is 1. Is 1 less than or equal to 0? No. Okay, return 0. Cool. We put in a 1. N is 1. Running total is 0. Counter is 0. Is counter, which is 0, less than or equal to 1? Yeah. Okay. Add 0 to the running total. 0 plus 0 is 0. Add 1 to counter. Okay, it's 1. Is 1 less than or equal to 1? True. So add 1 to the running total. 0 plus 1 is 1. Add 1 to the counter. That's 2. Is 2 less than or equal to 1? False. Go down here, return running total, which is 1. If we go to 5, it's going to be 0 plus 1 plus 2 plus 3 plus 4 plus 5. That adds up to 15, and so on. Now, the reason I brought up the negative 1 is, well, okay, the sum of all numbers between 0 and negative 1. You might say, well, the sum really is negative 1, right? But we have to be careful here. And you could make an argument that it should be negative 1. Fine. But usually, when we say from to, there's a direction involved. Let me put it this way. How many numbers are there between 0 and 5? Let's say we're including all of them. Okay, there's 0, 1, 2, 3, 4, 5, right? How about 10? Well, now there's more that way. You notice whenever I say starting from and going to, there's a direction involved. Starting at 0 and going towards where we're going. We're always stepping forward by 1 when we're asking that question. So when I say starting at 0, okay, imagine I'm on a number line. Starting at 0, looking to positive numbers. How many steps do I have to take to get to 10? Okay, in this case, 0, 1, 2, we go up to 10. How many to get to 100? Okay, 0, how many steps do I have to go to get to where I want to go? Starting at 0, how many steps that way do I have to take to get to negative 1? Going that way. It's kind of like a inadmissible question, right? You can't get to negative 1 by going that way. So how many numbers are there between 0 and negative 1 to that way? Well, there's 0 numbers. You can't. So that's why I would say the answer is 0, because there are none. But if you really wanted to argue, well, maybe we should be able to look back, okay, fine. But implicitly, people always assume, especially in programming, people are always going to assume how many steps in the positive direction whenever you have a from and to. just as an FYI. Any questions about this one here? If you struggled with it, it's easy to figure out. The trick is the one and only trick. Later, grab a sheet of paper and a pencil, make a table of the variables, and keep track of everything as you go. And if it still didn't make sense, do it again. And if it still doesn't make sense, do it again. Trace through it by hand, it'll make sense. If you've come this far, it'll make sense. All right. Well, here's what we could do is n now when I run it, I mean, we're going to see a bunch here. Let's get rid of the asserts. There, nope. There. We can kind of see by printing out the values in the loop as we go. Well, n is always 5, doesn't change. Running total is 0, or no, what is it? Counter is 0, running total is 0. Counter is 1, running total is 0. It's kind of funny. You might be like, shouldn't running total be 1? Well, we haven't added anything to running total yet. Maybe if I put this here, there. Now you might like it a little more. We have to just be careful where you put the print statements. Shouldn't I have added anything to it yet? Well, not before I added anything to it, if that makes sense. So see how I printed out the values as we're going in the loop? This might help you wrap your head around what's going on. Any questions, anything? Thoughts, concerns, comments, points, observations? Nothing. So that means you all 100% absolutely agree and find this perfectly clear. Is that right? Say nothing if that's correct. Perfect. Nice try there. All right. Algorithms. I've talked about this before. Let's make sure recording is going on. Yeah. I've talked about this before, and I'll keep talking about it. The above function, now algorithms don't need to be functions, to be very clear, but the above function is an algorithm. Everything we've written so far is an algorithm, but sometimes it's easier to talk about algorithms once they get sufficiently complex enough that they're doing some interesting task. Everything you do is arguably interesting and whatnot, but like a function to sum all the numbers between 0 and n, that's like a nice functional unit of something, right? Like, obviously, there's several steps involved, and it's this nice abstract thing where we're like, okay, sum all that up. Like on the test, checking the mod 3, mod 5. What does it do? Well, it checks if numbers are evenly divisible by 3 and 5, or a factor of 3 and 5, right? It's like a nice, clear functional unit. Obviously, there's parts to it, but we could describe all of those parts with a nice, clean, succinct description of what it's doing. So it's a little easier to talk about those things in terms of algorithms because it's a little clearer, I think. An algorithm really is, at the end of the day, a series of steps such that you can follow the steps to achieve some desired goal. Without being like, technically speaking, no, for real, following a recipe to make cookies is an algorithm. I'm not being like, oh, if you stretch the definition. No, it literally is. It is. A recipe is an algorithm. Driving directions, it's an algorithm. They are. I'm not making a stretch of the word. That's what they are by definition. Although algorithms can be explained in natural language, like I can describe to you how to add up the numbers between 0 and n, computers don't like natural language, so we write like our algorithms in code because it's a little bit more explicit. It's a language we've created. Like programming languages are created for humans to describe algorithms to a computer in a nice, clean, formal way. It's a special language. In the same way that we've created like our syntax and symbols and semantics for like math that we've been doing since we were this big. We created this like language to describe things in a nice clean way. It's not a natural language, it's a more formal language, but it's like a specialized language, just like Python is. Now Python, Java, C#, they're all very similar languages, but the idea is the same. We've created this syntax that has semantics that it makes it easy for us to describe algorithms. That's it. That's like its purpose as a tool. And remember, computer code is not for computers, though. It's for humans. It's a human language at the end of the day that we've created to describe these algorithms. The computers, they like machine code. That's an entirely different thing. And we have programs that convert the like Python code to machine code. They are different. There's a relationship, but they are separate. Finding an algorithm to solve an arbitrary task is non-trivial. Some problems might have easier algorithms might be easier to solve than others. That's probably pretty obvious. And at the end of the day, you can literally make $1 million if you solve like certain problems. Like literally, like you will get paid. They will pay, like there is a prize. If you can write a nice algorithm for this, here's $1 million. Which at a time was a big deal. Today, it almost feels like nothing. So just as an exercise, and you know what, don't worry about writing it down. I want you to talk amongst yourselves. So if you're alone, go find a friend to talk to. I want you to take turns, and in some way, I want you to explain in English how to calculate the sum of all even numbers between 0 and n. I don't care if it's inclusive or not. Just explain how you would do that. But don't try to make it overly Python-y. Just explain how you would do that. And then maybe try again and explain it still in English, but try to be a little bit more Python-y. And then finally, do it another time where you make it quite explicitly Python-y. And I want you to see how your descriptions are changing and how they're actually the same. I want you to kind of get a sense of how similar and dissimilar they are. And seriously, talk amongst yourselves for a few minutes there. And get this like played out. Don't worry about the assert tests or anything. It's far too quiet in here for you to be doing this. Bless you, bless you. You're not You're not talking. Neither are you, neither are you. Seriously, this is way too quiet. Are you being mean?
How do I get in between, like Python and normal humans? Like, how do I
That's the exercise.
I don't know how to speak to a cyborg. I don't know.
Yeah, pretend he's a cyborg. He half gets it.
I've never met a cyborg before. Okay. Here, eat food. Okay. He'll be holding you. Cyborg. You're holding food? Holding it. This is Python. No. Just tell me what to do. Okay. Okay. Listen, you are a cyborg. You are amazing at that. So calculate the sum of all food.
All right, I'm going to assume you're done. It just got really quiet.
I'm just trying to think of a way bullshit or instruction. Yeah. Come on, I'm talking to a cyborg.
If it's 3, it should be 2.
Yeah. Oh, it said so. Yeah, that's fair. What I said. Calculate the sum of all even numbers. Okay, sounds good. You're gonna start from like negative a cajillion. Okay, from 0 up to 10.
Up to a cajillion? That's sadistic.
I started at negative 2 cajillion.
Okay.
Up to 10. Yeah, I did. I started at negative 2. Yeah. Okay. Calculate the sum of all even numbers from 0 to 10. A cyborg doesn't have to add things. They're smarter than me. Oh. Good job. You're very smart.
All right, hopefully you had a little fun. I mean, this is obviously a bit of a silly exercise in the sense that it's not silly in the sense that it's like informative and it's a good exercise to do. But what I always find, I remember I had a prof once that was, so there's this idea of pseudocode. So the pseudocode is, you look at, it's like code, but it's not like any particular language. It's somewhere like just slightly less codey than code. And I remember I had a math prof that was like, no, your code looks, it's too like Englishy. And then, okay, we'd redo it. It's too Englishy still. And you'd redo it. And he's like, that looks too much like Java. And you're like, oh, God. Right? Like, I think he was just having fun with us. Because it's kind of difficult, like, where is it, right? Like, how do you draw that line? Especially because, like, how formal you need to be. Well, not how formal, but, like, your syntax of a programming language, at the end of the day, is somewhat arbitrary. It's defined by who made the programming language. So it's always a little tricky. But, I mean, just as a point, like, what I would say, like, if I'm just speaking to another human, I would be like, okay, between 0 and n. So what you do is you start at 0, and you count up towards n, and every time, like, you just check, is each number, like, evenly divisible by 2? And if it is, add it to a running total, right? And maybe that's a little too codey, honestly. Like, look at each, and maybe I should say, look at all the numbers between 0 and n, and if it's even, add them together, right? Because another human would know, like, oh, if it's even, what does that mean? I mean, how many of you, when you look at a number to check if it's even, you can look at a number, check if it's even, and know if it's even or not, but you're not going like, 17. 17 divided by 2, it has a remainder 1. Ah, it's odd. No, you didn't do that, right? You just know, right? So you could talk to a human at a pretty abstract level. If I were to try to like narrow it down a little bit more, try to make it a little bit more formal, as I would say, okay, start at 0. You look at the number 0, you check if it's evenly divisible by 2. If it is, add it to a running total. And then you go to the next number, and then you check if that's evenly divisible by 2, and so on and so on and so on. You can try to cheese the exercise by saying, okay, start at 0 and count by 2s and add them all together instead of counting by 1. Why, are you laughing? Is that what you did? Yeah. Jerk, I don't know, you're trying to cheat. But I mean, there you go, it's a solution to the problem. And then of course, if we did it in Python, you would start defining variables. You'd define the function. You'd have a counter. You'd have a running total variable. And then you'd check, is that counter less than or equal to the number I want to go to. And then you check, is that number mod 2 equal to, right? So it's getting more and more specific. And that like specificness is to eliminate any ambiguity, because the computer's not going to assume anything. It can only assume exactly what it knows and what you've told it. It's not going to make any other conclusions, because a computer's a computer. It's not you and I. We don't have this like shared experience of basic mathematics where we can communicate at a much higher level. So you have to like narrow it down. All of those things are algorithms, but they are all described at a different like level of detail. And some level of details is fine for some contexts and not others. Is that clear? Does that kind of make sense? Hopefully it does. This isn't necessarily a very technical idea I want you to grasp. It's more of a big picture idea that's important to be aware of before we continue. It's kind of like a stake in the ground. Like, okay, we've learned everything so far, and that's all like formal Python, but like, okay, pause, and let's think of how this fits into everything else we're aware of. All right, let's continue on with talking about strings. Strings are actually kind of weird. Like, they were one of the first types we talked about, but strings are actually quite strange. Like, an integer it's just an integer. A float, it's a float. A Boolean's a Boolean. But like, strings are funny because, like, classically speaking, there's another data type. Python doesn't actually really use this. But like, if we were if this was Java or C or C++, there's another data type that we haven't talked about, and it's an individual character, a letter, basically. So we have characters. Now, a character is like a number and a float and a Boolean in a way that, like, we would call these things like primitive types, which is kind of like a big word that's kind of hard to nail down what it means at this stage. But like, a computer is designed by humans for humans, and they've decided at one point in time, okay, if I want to store a number in a computer, I can put in, like, imagine, okay, we have memory, right? We have, we have computer memory, okay? So imagine that a computer, you all have computer memory on your computer, and the more RAM you have, your computer's better, right? Yay. Imagine this room, all of these seats in here, is a memory location. Now, there's more nuance to it, and we're going to get into these details a little bit later. But imagine each of these seats is a nice division of computer memory. And if I have an integer, and I say, okay, I want to store this integer in memory, perfect. An integer fits in one of these seats perfectly. So you could all be integers if you want. You all sit in a seat. If you're sitting in one seat, you take up the one seat. You're stored in the amount of room an integer needs needs to be stored, right? Each integer fits in one of these seats nicely. Each Boolean sits in one of these seats nicely. Now, as an aside, they actually do take different amounts of space, but for the purposes of what we're describing, let's assume they all take the same amount of space. A floating point number, they all can fit in one of these seats really nicely. An individual character fits in one of these seats really nicely, right? So you might be an integer, you might be a letter, you might be a float, you might be a Boolean. It's fine. You all fit in a memory location really nicely. Here's the problem. If I have the string hello, well, hello has H-E-L-L-O, 5 letters in it. And an individual letter can fit in one seat. But I got 5 letters. And I can't put 5 letters in one seat. That ain't happening. So we have to play a little game. We have to use a trick. And the trick is, no, you still store each letter in its own location. It's just you set aside a letter, like you set aside a seat for each letter. So here I would have like H-E-L-L-O. Or I guess for you, H-E-L-L-O. There'd be a single letter here, a single letter here, a single letter here, and here and here. But when you put them together, it makes the whole string. So a whole string, really, classically speaking, it's a little different in Python and a lot of modern languages, but the ideas are still exactly the same. Classically speaking, a string doesn't fit into memory the same way an integer or a float or a Boolean does, or an individual character. We have to get creative. It's almost like this meta type. It's like this type that has a little bit more to it than your integer and Boolean and float. Is that clear? Hopefully you can get each character can fit in a seat, but I have 5 characters. In fact, it's worse than that, because how big can my strings get? Pretty damn big. Hell of a lot more than 5 characters. You could load a whole book up and store it in a single string. That takes up more RAM. You could have a string that takes up 0 seats. Okay, fine. The amount of room a string needs is variable. But every number fits nicely. And do not confuse the number. This is very important. Do not confuse a number and how we write a number. The number 10 doesn't take up more room than the number 1. For us, we're well, we need 2 symbols. We like base 10. That's arbitrary. But the value, what 10 means, it takes up that idea is the same. It's just an integer. So even though that an integer might have more symbols for it, to a computer, they all take up the exact same amount of space. For us as humans, they're different because we write them different, but a computer doesn't write it like that. They have to, when they want to display a number to us, it has to decode it to show it to us stupid humans. So is it clear that clearly strings are different? Yeah. Now, that said, I could have the string 100, which would be 100, but that is very different than the value 100, which can just sit in one seat nicely. What's interesting here, too, is I can actually even, and some of you have done this accidentally in lab, you can index strings. You could go to the string and be like, hey, tell me the character at position 0. And remember, we always start counting at 0. And that would mean, if I had hello here, H-E-L-L-O, it means go to the beginning of the list and give me, or the string, pardon me, and give me that character. Oh, it's an H. Then I say go to 4. Okay, well here I guess the string is H-E-L-L-O, comma, space, W-O-R-L-D, exclamation point. So H-E-L-L-O, comma, space, uh-oh. Well, it must wrap around here, I guess. I could just keep going. Okay, go to the beginning and take 4 steps. Okay, 1, 2, 3, 4. Well, that's H-E-L-L-O. Okay, that's a lowercase o. Awesome, yeah. Which is cool. You can't index an integer. That doesn't make any sense. But a string, you could say, give me the individual letter at this position, at this index. Any questions so far? Yeah, okay. The index beginning at 0, not 1. There are historical and really important engineering reasons for this, and there are plenty of other languages that start at 1, but they're terrible. This can feel tedious to new programmers, but there's actually there's so many good reasons why we like starting at 1, and we will see as we go. Yeah? H-E-L 0, 1, 2, 3, 4. Because we start at 0. Yeah, that's why. Yeah. 0 is H, 1 is E, 2 is L, 3 is L, 4 is O, 5 is comma, 6 is space. Yeah. We go here. And you'll be like, oh, it's nothing. And you're like, well, if I highlight, you can see that there is actually something there. It's just, you can't see it. It's because it's a space, right? What do you think is going to happen if I say 10? What about 20? It's saying there's no room here. There is none. The string is only length, hey, you want to see something cool? Check this out. Here's a spoiler for what's to come. L. And now what's it mad? Oh yeah, it's still mad about that. It's 13. This string has 13 letters in it. 0 through 12, because we start at 0. So there's 13 individual letters. And so if I say, hey, go get letter 20, Python's like, what the hell? That's not a thing. Now, interestingly enough, by the way, here's a little trivia before we wrap up for the day. In some older programming languages that work the same general idea, what it would do is it would go to the memory address of where the string starts, right? And let's say your string was hello, H-E-L-L-O. And let's assume that the indexing goes like this. Like if I were to go to like, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Like we just keep going like that up, okay, let's say. For you, is that, yeah, that makes sense. So if I say, in Python, if I say go to index 0, well, that's H. Index 3, 0, 1, 2, 3, H-E-L-L. It's an L, right? If I say go to index 10, it's going to go, that's not a thing. It ends here. I can't, hello doesn't, I can't. In C, it goes, okay, yep, yeah, oh. Well, that's a happy face. And you're like, no, it's not. And it's like, well, that's what was there. It went and looked at that. It's like telling it to go look in that mailbox. That mailbox might have nothing to do with the string, but whatever's in that mailbox, it's like, I found it. That's what it's doing. Now, that's very unsafe, and that's actually how a lot of old hacking would work, right? You'd kind of mess around, and you can go to different chunks of RAM and start messing with what's in there. And here's another interesting thing about Python. This is just syntactic sugar. You can't do this in many other languages. What's at index -1? Here, let me get rid of that. It's the exclamation point. It's the last letter. -2 is the second last letter. -3 is the third last letter. This is just syntactic sugar for the following. Nope. Where you say, okay, give me the length -1, that would be the last letter. Because remember, the length is 13, but there is no index 13. It ends at 12. All right, we'll pick up here on Tuesday.